Hi, it's product repair time. We've got more studio monitor speakers. I've done a few studio monitor speakers before. They're always fun and interesting. So this time we've got JBL Series 3 LSR308s for those playing along at home. These are the new 3 Series JBLs, and by most accounts, they're actually really excellent studio monitors, at least, for the price. But one of them's working, one of them's not. And in comparison to my focal CMSs there, the focals are better. It's cheap particle board rubbish, not the die-cast alloy focals there, Bobby Dazzler. Anyway, this one here is not working. Check it out. It looks like, something out of the Batcave. Looks really interesting. These are rear-ported 8-inch models. You can get them in various smaller sizes. This is a larger one. They're actually rather huge, and the tuned rear vented port on them, apparently that's like really whiz-bang designed or something like that. And it's got all the requisite stuff down here. Made in China, of course. Grown. Anyway, a linear spatial reference bi-amplified studio monitor. Fantastic. Anyway, it's got various trims and things, and I have tried it through the TRS balanced input, and as I said, this sucker here doesn't work. This one works a treat. Let me just switch it on, and there's no hum, there's no loud bang. It doesn't smell bad. Always do smell test first. Maybe it will be when we open it, who knows. But anyway, LED comes on and then it starts to flash. So I'm not sure what that means. I guess I should RTFM. But the other one doesn't do that. It just stays on. Now this is really weird because I downloaded the manual for the 308 and I couldn't find any reference to blinking or flashing. It was just the power LED, and it's got an auto, it takes a couple of seconds to turn on. That's like a de-thump thing. Seems to be taking a while though. I couldn't find anything about this flashing in the manual, but then I found the LSR308P, which is the Mark II model of this, and it actually has an auto power down function. It's a microprocessory controlled thing. It's got to be intelligently controlled. You set the switches on the back. Apparently when you turn it on, you can enable or disable the auto power off feature, so it doesn't actually produce hiss or anything like that when you've got no input signal. I've done a video on hiss in studio monitor speakers before and why that happens, which I'll link in down below at the end if you haven't seen it. It's interesting. Anyway, these are not the Mark II models, so I don't know what on earth this flashing LED is. Let's open it up. So yeah, I've set all the same input parameters as the other speaker and volume, max volume, and the other speaker works fine, and this one I just get no audio out. So that is the symptom of this thing. So these will just be going into chipboard, cheap as chips. You're all weak. All right, well this... Oh yeah, she comes out easy enough. Yeah, not much lead length. I see the felt and everything inside. There's our special whiz-bang tuned port on that baby. So all you tuned port aficionados are all going wild. So, and by several accounts, it's actually extremely well designed, apparently. Gives a nice flat response. There you have it, we're in. They kind of stopped spray painting around there. But inside, oh, look at this, spared no expense. They've got the acoustic foam kind of stuff, dampening foam, whatever you want to call it. And some nice attention to detail down there. Look at the speaker wires. I've got some ferrite clamps on that. That's really neat. Anyway, that board, we'll have a better look at that over time, but that looks nice and jazzy, doesn't it? Wow. And there you go, it looks like we've got an ABS front panel, so yeah, that's not the best, is it, for rigidity and stuff like that. Look, I'm not going to bother to take the front panel off. There's the woofer, and the tweeter down in there. Doesn't look very impressive, does it? Yeah, it's neat and tidy. Yeah, I'm actually rather impressed by the neatness of this. We have our gunk, of course, not like the black gunk of death you get in the KRK Rokits, or rockets, I call them Rokits. Anyway, check out the power supply input. Choke arrangement there, that's very nice, isn't it? Some Y-class caps going down the ground there. Speaking of which, we've got 2 earth points. One's there, and the other one is down there. There's 2 wires going off. One actually pops up over the top here, and it goes soldered down into the PCB down there. Thank you very much. Anyway, they got a switch-in supply on this thing because, well, its mains are straight in here. And I do actually like the arrangement here. They've got the mains input IEC connector board down here with the cable coming up. That's all, like, it's all very nice. And then a big, plastic standoff because you've got to have the depth of the XLR connectors and stuff like that. So they'll be in there somewhere. Not sure how they're all connected. Oh, okay. I think I might see it. Probably that is the interconnect to go down to a board down the bottom, I would, inside the plastic enclosure. It just looks nice and neat and tidy. Anyway, we've got our 240 volt mains in, none of that 110, 120 volt rubbish. 4 amp fuse. We've got a thermistor there in line. That's not thermal adhesive. I think they're just stopping it flapping around in the breeze there. As I pointed out before, all these nice common mode chokes and filter in here. Big ass full wave bridge rectifier. Look at that jobby. And that's our main input filter cap, 105 degrees. And who's your daddy? A Koshin. Don't think I've seen a Koshin before. Have to look them up. Well, they're a Chinese manufacturer, been going since 1984. I don't know. Leave it in the comments down below. Are they any good? And they've got Koshin down here on the secondary side as well. Actually, one thing I find a bit surprising is the lack of secondary output capacitance. I mean, yeah, we got that jobby, that one, and this one over here, just one. So I would have expected more than that. Anyway, I'm reasonably impressed by this board. It looks like it's reasonable quality. It's it's laid out quite well. At least care has been taken in it. So yeah, I think they know what they're doing there. But anyway, the first thing, of course, as I said, give it a smell test. There's nothing obvious. And then, of course, you look for the caps. And, well, there's no bulges in the caps. They're none of that polymer rubbish. They've got good old liquid in them. No bursties on the vents or anything like that. So that's all looking sweet. The primary side cap, usually they're fairly good. But yeah, the next thing to do, of course, thou shalt measure voltages. And luckily, we have voltages over here. Check this out. 3.3 volts and 5 volts. Why have we got 3.3? Because, look, it's a crystal. And sure enough, that's got to be a micro. I can't see it from here as an ST jobby. Why do we have a micro? And that obviously explains the flashing LED. Look, we've got another crystal over here. So this thing is just, even though this is not a USB, like, digital input thing, this thing has at least 2 intelligent doodads in it. Well, there's no less than 7 screws holding this board in, so somebody had fun. And yeah, I think I'm right about that connector. Yep, it popped off, and there you go. Oh, look at that. Nice. They're doing that. You'll notice that's got sort of like a foamy type surrounder about there. That's so that they get all of the acoustic sealing. They don't have it escape through the connectors. And by the way, I forgot to point out the acoustic seal sort of foam tape around the outside edges here. So yeah, a good part of speaker design is making sure you get a nice sealed enclosure. Anyway, it says dip in. That's the direction they want the board to travel inside the wave soldering machine when they do all the through-hole parts. Oh, and the back plate, by the way, is not mains earth grounded. It is output audio grounded. So there's the mains input board. As I said, that's very nicely designed. They've actually got 2 levels on that. One down here for the switch and one up here for the IEC input connector. That's just like, wow, spared no expense. And the bottom side of the board up here, you can see all of the residue from the dip soldering, the wave soldering process. So that's not going to cause an issue. But anyway, we've got a whole bunch of surface mount stuff on the bottom. Why you would, like, there's no shortage of room in this thing, really. So why you would put surface mount stuff on the bottom? They had to for layout reasons. Like, I don't, like, nah. It's not something I would have done unless I absolutely had to. Anyway, you can see that we've got some primary side switching stuff over here. This handles, that's the primary side switching controller, and a whole bunch of passives and a few little active diodes and trannies and stuff down in there. So anyway, the silkscreen's reasonably informative, and I love the fact that they've actually put the silkscreen of the parts on the top actually on the bottom, so you can actually see even though the parts are mounted on the top side. Nice. And underneath this heatsink, I can only presume that that's our main power amplifier. I see, it has to be. Looks like they got the crystal. I thought it was going over here. Crystal is for under there, so I think we've got some intelligent Class D type doodaddy amplifier here. And there's no way that's just like an analog Class D amp. That's got to be like some DSP type intelligent thing, because you wouldn't need the crystal otherwise. So yeah, I think this is doing a lot of smarts. I mean, that with the ST Micro down there, and what's that little jobby down in there doing? That's a Cirrus? That's Cirrus Logic. Oh, does this thing actually sample the inputs and then process them, and then why you'd want to, I don't know, because it's got filtering, but I would have assumed that was like analog filtering, but maybe they're doing that digitally. Like, based on what's coming in and out of here, it's not much. Is it all digital? Wow. So yeah, I reckon under there is some sort of DSP Class D amplifier. Oh, it's a bit rude, isn't it? And yep, that's a Cirrus Logic 5341. That's an audio grade ADC. So that's clearly taking the inputs from here and just basically straight in, sampling those. So all that analog stuff, you know, the high frequency, low frequency, adjust and all that, that's all done in software. So the micro, which is an STM job down here, nothing special about that. That's just like reading the input switches. Maybe it's like setting like the coefficients for the as I said, almost certainly a DSP Class D audio amplifier under here. We'll take that off in a minute, and I'd say the crystal is probably shared between both of those. So yeah, that's just analog to digital, digital out, straight into there, and then the micro here just tweaks some coefficients and does some stuff, and that's it. So it's like a software-based speaker. It's, quite frankly, it's rude. And there's a test connector down there. It's got like a reset line. It's got boot. Can we actually, maybe we could reset the processor? No, but it seems to be going through. Like the processor's almost certainly working. You're not going to get the power on delay and then the flashing LED when, if the processor's not working. So that's fine. But obviously something wrong with the sampling or the output. It could be just a blown output driver or something like that. So yeah, I mean, we're basically going to have to do some digital debugging in a bloody studio monitor speaker. Sacrilege. What's the world coming to? And sure enough, there it is. That's an STA350B with a newfangled DSP thing. It's some fancy 50 watt per channel digital audio system. Yeah, okay. Anyway, yeah, it has a heatsink on top. Doesn't have a thermal pad on top though. It's I believe it's got a thermal pad on the bottom of the package, which will no doubt be soldered down to the ground plane down there. You can see some thermal vias either side of there, trying to stitch that through. But yeah, they put a heatsink on top. So I don't know if the other models in this series would use the same board, because the silkscreen on this says LSR308. So yeah, I don't know. Presumably like exactly the same architecture, but probably reduced power. Anyway, so we can safely power that up without the heatsink. It'll probably work up to 10 watts per channel or something without the heatsink, because you've got to remember, this is not a linear amplifier. This is a Class D amplifier. That's because I'm sure at 50 watts plus 50 watts, you don't need much of a heatsink. It's going to, the Class D audio amps are very efficient. So yeah, it's got all sorts of DSP goodness in there to do all manner of evil things. Oh goodness, come on! Like the big linear transformer and just big Class A amp. Piss away that power, please. So we'll start by measuring the digital power supplies. With any luck, that'll be easy peasy. 3.3 and 5. Alright, so the digital supplies are good. Let's go for the other stuff. We've got a plus 8 volts there, And the analog supply rails, these newfangled chippies, they don't have your traditional plus minus supplies. It'll just have one rail, and there it is, plus V. Data sheet for this sucker says like a maximum of 30 volts. So I don't know, it could be like 24 volts or something like that. 7.96, good enough for Australia, and 26. Yeah, okay, that sounds fine. They've got another link there, but I think they're actually connected together. 26 volts. So we've got our main supply for this. The power chip actually needs lots of supplies. It needs digital supplies. It needs PLL supplies. It needs the main power supply, of course. So yeah, everything's. I think that's all she wrote for the rails on there. So I don't think it's a power supply related problem. And just to prevent any brain farts where I accidentally touch the main section while I'm troubleshooting the low voltage side of this thing, I've just got an old food container, takeaway food container, wax over the top like that. It's a Bobby Dazzler. That'll just stop me, accidentally brushing the live heat sinks. All right, so it's time to get the scope out, I think. And let's have a look at our lead line there. There you go. Blinkety blink. So our process is doing something. Now, as you saw before, there is a reset line there. I'm going to probe that reset line, and that is normally high, 3.3. So I wonder what happens if we just, it's probably got like a power up reset thing, but I wonder what happens if we just reset that. So the way that you can do that, use your multimeter as a shorting probe, whacking in the milliamps, and then just short it out. Going to have to use my third hand here, which is the scope, just holding that probe in place there. And let's reset this sucker. See what happens. Yep, low. And then it should take that few seconds to reboot. And will it come good? Yeah. Oh, there you go. Oh no, there you go. Constantly on, and then it started to blink again. Didn't expect it to fix it, but yeah. And that crystal down in there for the TDA output amp, and also I believe the Cirrus Logic chip there are 12.288 megahertz. Yep, no worries. Now, there's a TX and RX on this little connector down here, obviously like, probably some sort of like test connector or something like that. And no, I can't get anything on there when I'm booting up or anything like that. There's just no activity. Now, I'm starting to realize, okay, so the processor's obviously working. The clock up here is working. So you've got to presume that, I haven't actually probed the pin on there. It's a real pain in the ass fine pin pitch. It's like, what is it, 0.35 millimeter pin pitch or something really annoying. I'm actually going to assume that because we've got some input circuitry, maybe the signals, maybe all this digital stuff is all just fine and dandy, and the signal's not actually coming from the PCB down in the bottom. We've got to have some sort of like a preamp thing down on that bottom board. So I might just take it apart again and actually try and get inside that sealed enclosure to see the PCB down in there. We could chase a red herring down a rabbit hole on the, debugging all this. Imagine, starting to have to, figure out the I2S clocks, trying to measure all that, probing it's really tricky and things like that, especially when you're trying to shoot a video, by the way, just saying. Troubleshooting ain't as easy when you're trying to shoot a video at the same time of it. Rather than just go down that rabbit hole now, I think it's worth seeing if we're actually getting the signal out of here. Now, I'm actually feeding in a 1 kilohertz tone, and I believe it's that pin down in there. Looks like it's that pin down in there that then comes out into here. So that, I believe that's our input, because everything else is like, look, power supply. It'd be that 8 volts that we saw, that we measured before. So, yep, that's going into there. Everything else is ground. These are like the digital outputs. So, and ta-da, there it is, because someone could have blown the snot out of that input. So, yeah, you never know. That's just the switch board, so nothing doing over there. But certainly we have an input amp down here, and it could certainly just be that board. That'd be nice. We can isolate that. But hang on for a second. That doesn't explain the flashing lead, does it? We had a blown input preamp, then that, you know, it just simply wouldn't work. The LED wouldn't be flashing. I'm going to rule that out. Anyway, no surprises for finding a JRC, a Japan Radio Corp amplifier on the front end. But that, you know, there's no blowholes in it. It's not like somebody's, you know, fed 48 volts phantom up its clacker or something like that. No, it's all good. So I'm just going to go in there and probe the ADC here just to see that it's like outputting stuff. That's not too hard. You don't even need to know the pin out because there's a whole bunch of resistors over there, and I'm guessing that they're series resistors for the various I2S data and clock lines. So, get one side of the resistor. Yeah, look at that. That looks like a clock. 3.072 next to it. Yeah, that looks like data. There you go. That's just random. That'll change every time. Don't worry about the overshoots there because I'm using a hideously long ground lead. All we're looking for, we're not looking for signal integrity here. We're just looking for data. And yep, there it is again. The ADC is doing its business and outputting stuff. So there's nothing wrong with that. Unless, like, as I said, like the signal's not coming in. But that, even if the signal wasn't coming in, that doesn't explain why the LED is flashing, and the LED flashing comes from the micro here, and it shouldn't be doing that. And the flashing LED is only on for the power down mode on the Mark II model. This is not the Mark II model. I can't find any information on the flashing LED at all. I presume it's some sort of fault code. So micro's working, ADC's working, it's outputting stuff. But unless you want to decode the I2S data and stuff like that, which, you know, I don't want to go down that rabbit hole yet. So, I don't know. What's left? The output power amp? Okay, what I'm going to do now to see if anything's getting into, like the input signal is getting into the ADC and the ADC is changing. I've got a signal generator that's going to generate a 1 kilohertz tone. I've got it switched off at the moment. So this is the data that we get at the moment. I just want to see if that changes. That's fairly consistent, so let me play this and see if that changes. Then we know that our input, you know, it's getting into the ADC and the ADC is outputting different data. Yep, look at that. That changes quite significantly. Yeah, there's more solid data there. Yeah, look. So that means looks like, you know, there's nothing inherently wrong with the input amp. Something's getting through, and the ADC is certainly changing the data on the output. So it looks like the data is going to the power amp chip. So I would say the problem is with the power amp chip, but why is that LED still flashing? Why? Oh, there goes the phone. Right, so now we have to start suspecting the STA350 chip here because our ADC seems to be working. It's outputting data, so we're getting no audio out is our symptom. Now, two lines that I'd immediately be interested in are, like, is this chip being shut down? Now, there's a reset pin at 31 here. This is where the datasheet kind of sucks. It doesn't really tell you. You have to assume that it is positive polarity because it's not a not bar, so there's no, it's not, you know, slash reset or reset with a bar. So you have to assume that it's a positive going reset line. So if it's high, it's reset. If it's low, it's fine. And then this int line here is actually an interrupt line. This is an output, and it's a fault interrupt. And the datasheet doesn't go into detail of this. And once again, it doesn't tell you the polarity of this thing or what it does, but it's basically a fault. So if there's something wrong inside the chip, this should give you, once again, presumably active high. It should give a high out. And as it turns out, if you look closely on the chip down in here, you'll notice that pin 32, there's pin 36. Notice pin 32, it's a little test pad right there. So I'm going to probe that, see if there's a fault. So let's probe that test point. And hello. Bingo, 3.3 volts, active high. That chip is giving us a fault output. So that's a fault interrupt. It's just active high. Maybe I can repower it. So let's leave the scope on there. Oh, there we go, it's drained. And turn it on. It's low. And then high, low, high, high, low, high, low, high. So, yep, it's giving a fault output. There's something wrong with that chip. And just for good measure, I'll measure that reset line. It goes to our resistor here. And it's also high. Like, I assume that the fault interrupt goes back to the processor, it's reading it, and then it goes, okay, there's a fault, well, I'll just reset the CPU. So here's the reset line. It's obviously under active control, low, high, low. It seems to correspond to that fault interrupt line. So, yeah. So yeah, I can only really come to the conclusion that the chip is faulty, and it's got, you know, extensive DSP and diagnostics and stuff in there, and it's reporting a fault back to the processor. The designers have implemented this properly, and they're actually reading the fault interrupt line, and the processor's going, well, if this thing's saying there's a fault, then I might as well reset it just so it doesn't blow up or something. Yeah, it doesn't, like, it stops driving, it disables the outputs. So I presume that's what's happening. And for a second there I thought, well, maybe, just maybe, one of the speakers might be at fault and, I don't know, shorted coil, something like that, and it might be detecting a shorted load or some other thing, because if you look at the data sheet, it says about this fault interrupt line that it does, you know, various like over voltage and over type protection and stuff like that. But no, just repowered it, and the light down in there, you might be able to see it going flishy flash. So no, wasn't that. Right, so what's actually causing this problem? Well, we don't exactly know, because there's just not enough detail in the data sheet to know exactly what's wrong. Apparently you can actually read out some registers and stuff like that, but obviously we're not going to go to that effort. So basically it comes down to two things: whether there's something internal to the chip, like there's some blown output MOSFET or something like that, and it's actually detecting that, or whether or not it's something external. Now, look, we've got some ceramic caps up here, and of course I've done many videos on ceramic capacitor failure and things like that. Very fascinating stuff, by the way, linked in at the end and down below if you haven't seen it. And there's some like on the speaker outputs here, so like maybe something could be loaded on the output, something like that, might have a short in a cap. So I'm going to get this board out again, do some visuals, of course, and then probably start just, probing around just to make sure impedances are okay with various caps and things. There's not much else that can fail. There's the electrolytic there. I have actually measured the ripple on that main supply rail, and there is none, so it's just fine. So yeah, I'm hoping it's external, because I don't want to have to suck off this thing with the pain in the ass pin pitch and the thermal pad down the bottom and actually replace that. That'd be a bit of a kick to the guts. So yeah, I'm hoping that it's external, but Murphy. And there's some of the caps on the bottom. So yeah, you just want to go around, make sure none of those are shorted. Like, opens aren't going to cause a problem, because I'm going to presume like it's some sort of that's measuring about 9 meg, by the way. It's fine. So opens aren't going to be a problem, but if something's shorted, then that could cause a problem. There we go. There's 4.7 ohms. What's that value there? I can't see it from here. And no, this one over here is a matching 4.9 ohms, so I'd say that's just hunky-dory. All right, well, I've measured every cap in there, and nothing's shorted, so with the power rail fine, I assume like 26 volts is okay, with bugger all ripple on it, no external loads. I get the same fault with or without the speakers loading it down, and there's no external impedances to load it down. You've got to say it's got to be internal to that chip, because all the external supplies are fine, and yet it's reporting some sort of internal fault back, which is then in turn, I believe, so I haven't checked the timing of this, but I believe that this thing reports back and gives that interrupt fault back to the CPU, and then the CPU goes, oh, interrupt fault, okay, reset and shut down. So that's why we're getting no audio. So now I'm thinking, well, it can't hurt to override the reset on this thing. Just ignore the interrupt output, but maybe either break, well, you probably, I don't like to force it, but the reset pin on this, because it could be driven directly from the micro, I don't want to short out the micro, but, well, you could, you can force it low instead of high, but maybe I cut a trace, or if I'm lucky, there's a series resistor in there somewhere that I can just lift, and then tie the reset line permanently low and see if the audio comes back. No, worth a shot. Because really, without doing that, I'm running out of ideas. The last thing would be, well, it looks like that chip's at fault. I've got enough evidence for that, so I'd have to order one and replace it. So, yeah, last-ditch effort. Okay, I've traced this out. Now, the reset pin here goes over to this resistor here, and which goes through a via down to the bottom side, which goes to a cap to ground. So obviously that's how they're doing the power on reset, but then it goes through the resistor, and I can buzz that out to pin 24 over here. There you go, pin 24. So that is driving the reset line. So I can simply remove that resistor, and, well, the cap is not exactly tying it to ground. It'll tie it to ground on power on, but then there'll be nothing holding it to ground. But then I can just put in a little mod wire to just short that sucker to ground. So it would be safe because it's through a 1K, so it wouldn't be shorting out the output of the chip. So the other side of this resistor over here, I can simply short to ground. That capacitor on the bottom, for example, I can just put a shorting link across that cap. Bob's your uncle. And one little bodge link. Let's go. And of course, we're still getting the blinkety-blink light in there because we haven't stopped it actually reporting that fault back. So we could actually break that fault interrupt line to actually stop it reporting that back. Actually, I could have done that. I could have just broken the fault interrupt line and then left the reset line. That's actually another way to do it. If I want the chip, if the chip doesn't get initialized properly because of the reset line, yeah, come to think of it, probably should have done that. Yeah, let's feed some signal in. And nope, I'm twiddling the knob and nothing. Well, didn't really expect it to work, but it's worth a shot. Takes like a second to do. Well, here's a plot twist. That test point we've got there, which is the fault interrupt output pin, it actually doesn't seem to go anywhere. There's no corresponding via under the bottom of that. I've looked fairly carefully on both sides to try and chase it out. The output pin is just going to that test point, and that's it. So that interrupt pin is not actually going back to the micro. So the micro is not actually detecting it via the interrupt, but as I said, there are registers inside that it can actually read. So regardless, the interrupt is just to alert the micro. So the micro is most likely reading those fault registers and going, yep, there's a fault there. And it's just going blinkety-blink on the LED, and that's it. We know it's actively shutting down the reset line on that chip, but yeah, so there could be, it's pointing towards that chip. I've got nothing else. Nah, I'm done. I'm just out of ideas. It's got to be that chip. There's a failure in it. I can't see anything else. So everything is clearly pointing towards the STA350 chip here, but just in case, because there's a lot of pins on there and there's a lot of power supply pins, just in case I didn't actually get every power supply, I thought I'd go through systematically and measure all of the power pins. And this is where it gets really interesting because there's a few like internal voltage references and stuff. So let's go down, and the first one right off the bat, with Kamagata, this VSS pin 4 internal reference at 3.3 volts. It says it's an I/O. Anyway, that is supposed to be connected. Pins 4 and 5 are supposed to have a cap between them, and they're supposed to be isolated according to the schematic, like example schematic in there. So it's an internal 3.3 volt reference voltage, and I measure 25.7 volts relative to signal ground and 26 volts. So actually 26.2. So when there's a difference of like half a volt between these, but when I measure actually across the capacitor, across pins 4 and 5, the differential, then I actually get 0. So obviously something's been snotted internally, and this voltage reference is just cactus. So yeah, there's something seriously wrong. Anyway, the positive power supply rail, 26 volts, as I said, I've measured that. There's no ripple. on that. It's a nice solid rail. VCC1 is 26 volts. Internal VDD reference, internal reference voltage, another one. Once again, I'm getting 0. And again, there's supposed to be a cap between these two here, and they're supposed to be isolated. They're not actually, it's not actually ground. It's like an internal voltage, floating voltage reference somehow. And once again, the differential between those is 0, and the value on both those is 0 relative to signal ground. So again, I think that's been snotted internally. Digital rail's fine. Positive supply for the phase lock loop is fine, and the digital supply down here is fine. So yeah, there is something seriously wrong with that puppy down there. Something's happened to it, and well, no wonder we get no sound out, because that's the driver. That's got the 4 MOSFETs on the output, and that does all the driving. And of course, what is causing the error message to blink, because it might still actually be working, like the digital part of it might still be working, and it might be like outputting, still might be able to read the registers, or maybe that blinking LED says, oh, I can't read the registers from this thing, something's up, and that's the internal error code for this thing. Undocumented error code is to flash the LED on the front, and that tells you it can't read that chip. So yeah, that's pretty conclusive. I think we need a new chip. So yes, I guess we probably could have gotten to this point a bit quicker if I followed my own advice, and thou shalt measure voltages. I should have measured the voltage on every one of the pins here. It's really hard to probe these tiny pin pitches in here. You can really short stuff out, and you can destroy stuff that's not destroyed already. So you've got to be careful. That's why you actually probe the external components. You probe the external caps on here. You just look. I've got to look at this under like a ×10 magnifying loupe. I just use my macro lens for my camera, actually. This makes a fine, if you don't know, this is the macro lens for my camera. It's an Opteka ×10 macro lens, 62mm. You can get them in different widths for different cameras, and this is what I whack on front of my camera to give me all the nice macro close-ups that you see in my videos. But it makes a great little handheld magnifier. It's absolutely fantastic. Anyway, if we actually went in and measured all those internal reference voltages in there, then we could have known from, the get-go that there was something wrong with that chip. But, we measured all the main power supply rails, everything else, and you don't expect any, like there could have been like micro cracks on some of the solder joints, because this is a thermal part, it heats up and cools down and things like that. And probably at a pinch at this point, I might have like reflowed this thing just in case. But anyway, might take the board out, get a higher magnification on this, and just have a look at the joints. But I don't think it's that. I think the chip is just snotted. Okay, we have determined that the STA350 power chip here and DSP thingy is most likely dodgy, so we need a replacement for that, and ta-da! I've magically got some replacements from the world of DigiKey. This actually comes in 2 different versions, by the way. This is the 350BW, and it has the thermal pad on the bottom of the chip. They also do a version with a thermal pad on the top, depending on what heatsink solution you're using here. Is actually using the heatsink on the bottom, you can see, and all this ground plane and via stitching, and we can see that by the big thermal pad on the bottom, and that thermal pad will come in very handy shortly. So you're going to make sure you've got the right version. It cost me a whole $4 each for one of these things. I got 2 just in case, because, well, they had to come from DigiKey, and I had to order other stuff to make it worthwhile for the postage and everything else, and, well, And it came in the seal bag with our humidity indicator. Thank you very much. Humidity can be a problem. You may have to actually bake, if you're serious about your electronics production, that you may actually have to bake components before assemble them and put them through the reflow oven machine, because you can actually get very specific machines for doing this, for baking. Like you can put entire reels of components inside baking ovens to draw the moisture out of them. It's just so that if there's any moisture buildup inside the plastic package, then when you put it through and heat it up, it doesn't like form little air pockets and actually burst the chip and things like that. So, it's only a worry about, really production scale type stuff. Anyway, So how do we replace a thermal power SO package? In this case, it's a regular SO package, but it's got the thermal pad on the bottom. If it was just a regular SO package, then we'd just get the hot air on there and just, you know, heat it, put some flux on, heat it up, and then get our tweezers once it's all melted. Both sides are melted at once, and then you can just lift the chip off. Unfortunately, because it's a power package, there's a lot of thermal mass in all of this ground plane, not only on the top here, look at this solid fillet, you know, it extends all the way over the board, but on the bottom as well. Luckily, it's only a 2-layer board. It's even worse if it's like a big, huge multi-layer thing and it's connected to the internal layers, but there's, you know, a lot of thermal mass there. So you can try and do this with your hot air gun, but you've got to put a lot of mass into heating up all of the copper. Now, you can actually help this along by using a preheater plate, and you've seen me use it before. And the idea is you put your board on this and then you heat up the bottom, but it's going to heat up the entire bottom of the board, but that actually helps. By doing that, put extra heat into all of the copper on there, so then you require less thermal capacity in your hot air gun to actually you know, heat up all the other pads and lift it off. So that can be one way, but I don't necessarily want to like heat up the entire board just for that one chip. Now, another way to do this, because the designer of this board has very thoughtfully left off all of the solder mask there around this thermal pad, we can get a real big ass tip like this one. Oh, it's a monster. And if we put that on there, we can actually heat that up. And in theory, you can actually heat up from the bottom, you can heat up the entire chip, and then the heat will actually flow out into the pads here through the bond wires into the pads over here, and it'll melt everything. And in theory, if you hold it upside down, that chip could just drop off. But you require to pump a lot of heat in there. So yeah, we could do that, but there's one more method that you can look at as well. So another way to do it is to actually separate the thermal mass of the chip from the pads, so that you use different techniques to desolder the pads as you do the thermal pad, large thermal mass pad on the bottom of the chip. And you do that by getting a sharp X-Acto knife in there and cutting the leads. Now, you have to be careful. Like, there's pros and cons of all these techniques, of course, but if you actually get in there and cut these leads, then you can actually separate the thermal mass of this chip so that you can get in there from the bottom, as we saw before with the soldering iron, and then this chip, you can actually remove this without potentially damaging the more delicate pads on either side. Now, this technique requires two things. A, it requires your tongue at the right angle so that you don't cut any traces. Next thing is it requires a shallow angle like this. So if you've got like large components around it, like if this chip was facing not that direction, but was facing that orientation, I'd have a hard time getting in there with my X-Acto knife and actually cutting out those pins. Because if you have a high angle like that, you're going to put lateral force on those pins, and there's not much adhesive on each one of those tiny little pissant pads in there to actually stop them ripping off the PCB. And you've got to be careful not to cut the traces underneath, of course, but if you keep a shallow angle, you're pretty much guaranteed not to do that unless you've got really fine traces and you come a gutser because you weren't holding your tongue at the right angle. But in this case of this chip, it looks like all the tracks are coming off out of the track like this, and they've just got ground plane under there, so it looks like there's really nothing under there because we have nice good access, low angle access in here. This is a good candidate for cutting the pins on this and separating this. Fingers crossed, let's go. So the technique where you actually heat it up from the bottom here and just use the weight of the chip to have it drop off, and that obviously works better for like larger mass components, but smaller mass components, they may actually just hold on due to surface tension of the solder, not only the surface tension of the main thermal pad on the bottom of the chip on the other side, but also all of the individual surface tensions of all the individual little pads in there as well help to keep it on. And which technique you use and and the risk of actually lifting any of the tiny little pads on here, which is always your main fear, is lifting a pad, and then that just ruins your day, really. So the quality of your PCB material is going to matter, i.e. the quality of the epoxy adhesive used to secure the pads, well, the copper, bond the copper to the fiberglass material in there, and you can have different temperature and quality ratings and things like that. So if you get, you know, a really pricey consumer fruity motherboard, for example, that might have like a real high quality fiberglass materials, so you can really abuse some of them, you know, with heat right up the clacker for ages, and you're not going to lift any pins at all. But then you get a $2 farty novelty gadget and try and do the same technique on that, and bingo, all your pads are lifted off. So anyway, I'm going to get in there and I'm going to cut these pins off, and then hopefully this chip will just drop off when we heat it up from the bottom, and just clean off the more delicate pads. Got to keep the tongue at the right angles. Now, what you want to do is not scrape along like this, but just push down, and you want to get right in against the plastic package in there. You don't want to be doing it out here, because then you could put leverage on the pins and easily lift the pads. As I said, not a high angle like that, but a low angle, and use a sharp X-Acto knife. This one actually seems really tough. I haven't, oh, there we go. just had to get the initial bit. This is tougher than other ones I've done. Wow, yeah, this one's really tough. More force on those pins than I'd like. This one is particularly tough, and probably should get a new X-Acto blade as well, but I've used this one, and it hasn't been a problem with other chips. This one's just got real beefy pins on it. Yeah, normally it'd be much faster and more efficient than this. Trust me. There we go, that's better. Just needed some slicing action. But you don't, as I said, like, you don't want to really get in there and drag it across, because that can put lateral force on the pins. So you can see the exposed copper. Yeah, this pad on the end lifted up because there's no trace on there. That's the problem with those pads, but it doesn't matter because there's no trace on it. They're not as strong as the ones that actually have the copper traces coming out of them. There you go. You can see how we've sliced through those pins. I made a meal of the other side, but anyway, let's flip it over. So let's now try and heat this sucker up. Come on, fall off. There we go. Just dropped off. Ta-da! There it is. No worries. And there is our leftover pins. Yeah, one of them come off. Yep, and it's the one without. It didn't have any track associated with it. But now we can just easily get those pins off with our large tip. Just scrape it across and Bob's your uncle. Bingo, there we go. Got a whole bunch. The advantage of having a monster tip. You could almost do an entire chip at once. There you go. Yeah, you don't want to scrape across the pads like that, because as I said, that applies lateral force, and the adhesive can come a gutser because you're heating it up. And depending upon the quality of your PCB, you can lift pads. If that's not clean enough already, you could actually go in there with some solder wick. There we go, clean those. Look at that, sweet as. So let's just wick that. I think that's all pretty much gone. So there you go. Beautiful, isn't it? That's how you get a power pad chip off like that, with putting minimal amount of heat on the pads. Although we did lift one, so I've come a gutser, but you know, can't be helped. But often this actually can be a better technique than just trying to like heat up the whole thing. And you'll notice that we didn't heat up any of the other components around here practically at all. So nothing else is going to get collateral damage. There she is. There's the power pad. All the electrons are going to fall out. It's upside down. STA350BW. Genuine. And this one, you can see that we don't have solder masks between individual pads. So, yeah, we could get like a bridge short across there, but when we reflow solder this, but, you know, you can clean that up easily. All right, solder paste time. I'll do it with solder paste because you know, to get down onto that thermal pad, you can put solder on there and reflow it, but it's like lumpy. You've got to put it on first, and then it's lumpy before it melts. It's kind of like a chicken and egg thing. Oh, a bit too much there. Wow. Oh, that paste wasn't exactly lined up. That looks all right. Now what I'm going to do now is, this is tricky to get on camera. Now here's of course where we've got two options again. I can try and get my iron on the pad on the bottom and try and reflow it that way. Whether or not the pins will actually then melt as well, don't know. Depends on the thermals of the whole thing. Or we can hot air reflow from the top. But that's kind of like desoldering it. So I don't know. I think I might give it a go with the iron. There we go. Our pins are melting. Our pins are melting. Are they? Yep. There we go. Pads are melting. So that did get through to our pins. So maybe we could have just, instead of cutting. You can see though, the problem here is that it hasn't properly self-aligned because the surface tension of the power pad is pulling it north like that. It's pulling it upward. That didn't work. So maybe somebody didn't design the thermal pad properly on the layout, perhaps? I don't know. There we go. Okay, way too much solder, so we'll wick that away. It's no problem. So yeah, don't be afraid that you've shorted your pins. It's not a problem. Yeah, the alignment's not great, is it? It's really pulled that chip over. It's hard to get in here though. I've got these vertical components are in the way, but unfortunately, those pins are askew, but they're not touching. They're still soldered. No worries. So that, there's still a short there. So I made a bit of a meal of this one. This is not something I do every day. If you do this every day, you get pretty used to it. There you go. Sucked him. It is off kilter, but I didn't want to go in there and force the issue and try and make it come back. Those ones aren't touching, so it'll still be good. It just looks a bit how you're doing, but it'll work a treat. All right, now let's switch it back on. Before you do that, of course, you measure all the rails, make sure that they're not shorted, anything like that. Done all that. So we're looking for the lead up in there. Nothing yet. It's on. It's on. It's staying on. No more blinky blink. Like, I'm going to presume like it's some sort of, that's measuring about 9 meg, by the way. It's fine. Winner, winner, chicken dinner. That works an absolute treat. So it doesn't sound as good as my focals. I still like my focals, but yeah, that's repaired. Yeah, so there you have it. That is a very nice repair. That was an overly long video. You know, in real terms, this was probably only like 30 minutes of repair work. You know, it takes longer to shoot video and stuff like that. So in the end, it was just the power amp chip. But the interesting part is the journey actually getting there and actually troubleshooting and narrowing it down to pretty much guaranteeing that it was that chip. We measured all the signals going in, everything was fine. We measured that there were no shorts on the outputs and things like external components causing any issues. We measured all the power supplies and everything's just hunky-dory. We looked at the data sheet and it had this thing where it actually could actually read back fault registers. So that made sense with the flashing LED as an undocumented fault code. I could not find that anywhere on the interwebs. I guess here it is now. So a blinking LED means that it's reporting some sort of fault from the power amp chip. And you know, it would have been nice if they like told you that in the manual. I could have just went, yep, just replace the power chip, no worries. It's simple repair in the end, but I liked the process actually getting to this, and I sort of documented more here than what I would normally do. Like some of these things take, you know, 5 seconds, 10 seconds to check these sort of things, but I turn them into 5 or 10 minutes worth of dialogue just for commentary. So anyway, I hope you enjoyed that and found it useful. If you did, please give it a big thumbs up. And as always, discuss down below. Let me know if you like repair videos. Some of them aren't as interesting as this, even though it was a chip. This is fantastic that it actually went down this level, because when I got these speakers, I had no idea that they had this digital DSP rubbish in there. I thought, you know, it'd just be like an analog thing or a power supply fault, something like that. So, you know, not always we get this lucky with an interesting sort of thing where we have to deep dive down. And by the way, my Patreon supporters would have already seen this video, like, or at least up until replacing the chip, like a week ago. So I often put my videos, especially ones like this where I'm waiting for parts or something like that, I'll just upload a pre-edit to Patreon supporters, Subscribe Star supporters, forum supporters. Yeah, if you want to see that sort of stuff, I don't like plug my patron at all in my other subscriber stuff. But yeah, I occasionally post stuff like that. So anyway, I hope you enjoyed that as much as I did. That was fascinating. And yes, by the way, these speakers, they have the hiss in them. Probably the worst I've heard. They're supposedly really good speakers. Anyway, I've done a video on tweeter hiss. It's just, spoiler alert, it's the inherent noise floor of the amplifiers and the massive dynamic range and efficiency of the speakers in these things. So anyway, hope you enjoyed that. Catch you next time.